great pleasure this morning to welcome our speaker, Dr. Richard Norris. Now, many of you may know that he valiantly tried to speak a few months ago and was stuck on the southbound 5, I guess it was.
15, actually. 15,
okay, close. I knew I'd get something wrong this morning. And but even more grateful that he was prepared to come a second time and talk to us. He's a professor of oceanography at Scripps. He's in the Geological Research Division, and he's a very recent addition to the SIO faculty, and he has come from Woods Hole. Now, I was going to say something else, but I won't. And so, apart from having strayed to the East Coast for a number of years, actually he's a native Californian and was born in San Pedro. And he was probably destined to become a scientist because he comes from a family of academics, and his father was a very prominent professor of natural history at UCLA, and his mother was a botanist. Well, now he's a geophysicist, that's Dick. But his early career, I gather, was much more into forays and biology. I know you were involved in the Condor Release Program. That's the Condor Recovery Program, which I think is very exciting. I used to be working at the Tracy Avery in Utah, and we would see some of these condors in southern Utah. And also he was director of the Granite Mountain Reserve, and as a part of the University of California Natural Land and Water Reserve System. So he's a very interesting mix, really, between a geologist and a biologist. And really, by training, he's an evolutionary biologist. So he's really interested in how species evolve over time. And he's particularly interested in looking at the paleoceanography of warm climates in Earth history and the structure and dynamics of large-scale diversification in the history of life. And today, Dick is going to speak on explorations of deep time in the tropical Atlantic, deep ocean drilling, 2003. Dick, thank you very much.
Well, thank you very much. Yes, obviously I've had somewhat of an eclectic career, and it is with great pleasure that I have finally managed to turn up in front of all of you. I did, as Nigella pointed out, try to get here, I think it was last spring, when there was the crane that fell over I-15 and plugged up absolutely everything in San Diego. That was an interesting introduction to the nature of things here in San Diego. Let's see. I'm dressed up in a tropical fashion for a rainy day because I'm going to give you sort of an overview of an oceanographic cruise that I participated in last winter to the tropical Atlantic. And the idea of this cruise was to study past warm climates, super warm climates, as potential analog to what we might expect to see in the future with future global warming. And so this is a cruise of the Ocean Drilling Program, or ODP here, and it's number 207 to a place off of northeastern South America. Now, we set sail on a lovely oceanographic research vessel. I gather that you don't believe me when I say that the Star Princess here is the source of our vessel. Actually, this is in Barbados, so we set sail from Barbados to Rio de Janeiro. And interestingly enough, I think that we could have fit the entire drilling derrick of our particular vessel into the hold of the Star Princess. But our ship is a much more functional, if not quite as beautiful, creation. The blue ship back here in the background. And this is characterized by a big drilling derrick located in the middle of the ship, which the drill pipe actually passes through a hole in the bottom of the ship, which is prosaically known as the moon pool. All right. Now, one nice feature about this vessel is that when we were sailing on it, they installed this big dome on top, which allowed for phone calls to be made off the ship with regularity. That was a first for the ocean drilling program. Before that time, you'd spend 2 months at sea with essentially only email communication on an episodic basis. This is some of the crew. This is the scientific party, okay, of this particular leg. 29 scientists in total from all over the world. I think actually 9 different nations involved. Here I am in tropical fashion. I want to point out a few people. You'll notice that we have quite a diversity of ages, of obviously a lot of women involved as well. And we have this guy right here. This is Jochen Erbacher. He was one of the co-chief scientists and also one of the proponents of the cruise. And then Paul Wilson here from Southampton Oceanography Center was another proponent. The three of us wrote the drilling proposal, I think in 1998, to actually have this cruise drilled. So it took that long for the whole thing to work its way through the review panels and so forth to become a going concern. We also have David Mosier here. He's from Canada, from Halifax, and he was the other co-chief scientist. Now, Paul Wilson, as I mentioned, was one of the writers of the original proposal. We met in 1998 in Woods Hole, and it turned out that right after he arrived, we had a hurricane, and it knocked out our power. We were there writing our drilling proposal by hurricane lamp for a while. But it also had the felicitous effect of washing a whole year class of scallops up on the beach. And so we went out with our garbage cans and had this absolutely fantastic scallop feed while Paul was in town. Now, he happens to be working on a microscope, and this little tray here contains the kinds of microfossils that I work on. Nigella mentioned my interest in evolutionary biology. These little sand grains, which I'll show you some pictures of in a moment, contain a diverse record of deep sea biology and evolutionary history. And here are some of these things. So these are created by unicellular marine animals called planktonic foraminifera. The scale bar here is 50 microns. So these are the size of salt grains of very fine sand. And in this case, these happen to come from a time period about 90 million years ago when the tropical Atlantic was much warmer than it is today. The notable thing about these is that they're extremely well preserved. They actually look just like they died yesterday. So we can go and collect very similar kinds of fossils, or actually living organisms, from the open ocean today. Now, the nice thing about having really well preserved fossils is that they make their skeletons out of calcium carbonate. And we can measure various aspects of the geochemistry of this calcium carbonate to deduce the nature of the ancient oceans, particularly its temperature, the nutrient status of the oceans, things like this. For this particular cruise, we're primarily interested in the temperature record preserved within these microfossils. And here's some sort of evidence from this. This is geologic time here from the present back to 112 million years ago. And this little scale up here is the so-called oxygen isotope scale, which scales approximately with temperature. So we have cold temperatures over at this end, warm temperatures over at that end. The black symbols represent foraminifera that lived on the bottom of the ocean, okay, through geologic time. And you notice that today we have relatively cold bottom waters. They're around 1 to 2 degrees centigrade in the modern oceans. But back 90 million years ago, temperatures were much warmer in the bottom of the ocean, perhaps 12 to 15 degrees centigrade. Now, notably enough, we have various measurements here in these blue symbols and the red symbols of planktonic foraminifera that live their lives in the surface ocean of the world. And the ones that are shown here in blue are from chalky marine sediments or limestones. And for a long time, that has been our primary record of surface ocean temperatures through geologic time. And you'll notice that they give a very different kind of isotopic record or paleotemperature than these foraminifera that come from clays, okay, that are preserved within clay environments. In fact, that was one of the points of this cruise, was to go and drill a long section in the deep ocean from the tropics where we could get foraminifera out of clays. because the clay-hosted foraminifera are typically much better preserved, and they seem to give us much warmer paleo temperatures, okay, up around, would be around 32 to 36 degrees centigrade for the tropics 90 million years ago. And you'll notice that if we believe this red record here, that there really hasn't been a dramatic change in tropical sea surface temperatures over the last 100 million years or so. Now, why do we care about surface temperatures? Part of it is that, that we're looking at times in the past where we had super warm climates, okay, where the tropics were perhaps in the 30, 35 degrees centigrade range. That's nice sort of warm bathtub kinds of temperatures. And we want to understand the dynamics that lead to super warm climates like this. Okay. Karen Bice here from Woods Hole Oceanographic Institution is a climate modeler. She was also a participant in the cruise. And here you see her with some of the cores that we drilled. And some of her climate simulations show that if we look at the kinds of isotopic temperatures or paleo temperatures we get out of these foraminifera, which are shown in these symbols here, that they're typically much warmer than the modern temperature gradient as we go from the southern hemisphere to the northern hemisphere. So that implies that today we have tropical temperatures around 28 degrees centigrade, but in the past we may have had tropical temperatures as warm as 36 degrees centigrade. The problem is, how do we get such warm temperatures? What makes the world into a hothouse like this? And we think that one of the things that can do it is by adding a lot of greenhouse gas, okay, namely carbon dioxide, to the atmosphere. And here's some of our simulations. These are based upon climate models here, matched up against our paleo temperature data from foraminifera. And you see that if we get somewhere between 4,000 to 5,000 parts per million CO2 in the atmosphere, we can begin to match these warm tropical temperatures of the past. Okay, so this is a general sort of curve now where we have our temperature estimate. In this case, this is an average global temperature, so it doesn't reach the peaks that we saw for our tropical data sets. And here's our estimate of how CO2 has changed in the atmosphere over time, starting off perhaps as high as around 4,000 parts per million in 100 million years ago, and declining to the present 300 parts per million, okay? And the key thing is that we know this curve only approximately. We're trying to refine that by carrying out more deep ocean drilling. So our effort was to go right here to a little bump off of northeastern South America called Demerara Rise. This is a reconstruction of the plate positions, of the continental positions as of 92 million years ago. And you'll notice that this little piece of South America was quite close to Western Africa at this time. The tropical Atlantic was a much narrower basin than it is today. And that will be relevant later on in my talk. Okay, so here's a view of what Demerara Rise looks like today. This is French Guiana down here, and this little bump of continental rocks that are now subsided below sea level is where we drilled, right in this area. All right, this is the JOIDES resolution in its white phase, all right? As of a couple of years ago, it's now has, of course, been painted blue. And it consists of a big helicopter landing deck on the aft end of the ship, which regretfully we ended up using twice on our cruise to helicopter people off the vessel. One of them was our chief driller who had a heart attack as we were coming into Rio de Janeiro. And so he was saved by the fact that we had a helicopter landing pad that they could get off of. We also have stacked back here a big pipe racker that holds about 6 to 9 kilometers of drill pipe, so that we can go from the surface of the ocean and drill in very deep water, in the deepest, some of the deepest parts of the ocean. This is the drilling derrick that you've seen before, with the drill pipe going through the center of the ship. The scientific laboratories are here for all 29 of us scientific staff. And then in the forepart, we have the galley and the crew quarters and so forth. These are really the most important people on the ship, okay, are the drilling crew. Many of them are from the Philippines. This fellow back here plays in a band called the Commodores when he's 2 months at sea, or 2 months back from sea in the Philippines. And that's amazing. They're amazingly intimidating kinds of characters, not because they're not nice, but rather because when you go down to the weight room, you see how they have set, all the machines to some appalling weight that you cannot even begin to budge. But they are amazingly strong guys, and they move these pipes around, these big, heavy weights that if they did it wrong, they'd kill themselves, basically, and they do it with terrific finesse. This thing here is so-called top drive. It's a motor that actually rotates the drill pipe and allows us to drill into the ocean floor. And there you actually see the drill pipe here as well. Now, the aft end of the ship, this is the drilling deck that I just showed you a picture of, and back here is this pipe racker where they haul these big 10-meter long pieces of pipe out, just whip them up, and in the space of about 2 minutes, they have this thing pulled up into the drilling derrick and then screwed together, and down they go. And so they can put together the whole drill string, say 3-4 kilometers of drill pipe, in the space of maybe 10 to 12 hours. It's just amazing what these guys do. This is the working end now of this drilling system. These are big roller cones, big drill bits that have these lumpy things on them that actually grind their way through the rock. And there's an aperture in the middle here, which is about that big around, I suppose, and that's what receives the core. So the idea is you're not trying to just grind all the stuff away. You actually want to get a record of the rocks and the mud at the bottom of the ocean. And so that aperture allows the core to rise up inside the drill pipe as you drill down, and the core is captured by a plastic liner that can then be pulled via cables up the inside of the drill pipe. So when we want to recover a core, we don't have to pull the whole drill string out, okay? We just haul the core right up the inside of the drill pipe. Now, of course, that would all be for naught if we didn't have a very important piece of technology, these little things right here, which are called core catchers. And they have little metal fingers on them that open up like this as the core is being pushed up inside the drill pipe. And then when you go to pull the core up to the deck, they snap shut and keep the core from falling out the bottom. All right. Now, the scientists are not typically running around on the rig floor. Instead, the rig floor is back up here. Instead, we are standing around at what is also prosaically known as the catwalk, okay? The place where we all parade for each other and take a look at the core when it comes out. And here I am standing with various other scientists waiting for the core to come out of the rig floor. The core looks like this. Here's this plastic pipe here. Here's Jochen Erbacher, our friendly co-chief. Paula Weiss, who's a core curator on our particular cruise. And we examine this core when it comes up, and then we cut it up into short sections that we can easily handle, because the pipe itself is about 10 meters long, and therefore you can't haul that into your laboratory very easily. Now, we as paleontologists, that is myself, this fellow here, Hiroshi Nishi from Kyushu University, Woody Wise from Florida, we have the pleasure of examining the core first, okay? Before anybody else gets their hands on it, we get to run off with a little chunk of mud like this and run down to our paleontology laboratory, which is shown here, okay? All of us Desians of the deep, with our microscopes all set up, ready to look at the kinds of microfossils that are present in those samples. We have to wash them, in my case, through various sieves. This is Danielle Danelian, who worked on radiolarians. I worked on forams. Woody Wise and Jorg Motterlose were nanofossil experts, and I'll tell you about this in just a moment. In any case, we'd wash our samples through these sieves. Sometimes it would make for rather interesting looking concoctions on the whole. We discovered later on that just household bleach was just the perfect thing for digesting some of these samples. And the idea was to get out these sorts of microfossils. So we have foraminifera here, up there as well, these beautiful diatoms, okay, and also these little spiky things called radiolarians. And in addition to that, we'd also find at a much smaller size scale this is a 10 micron scale bar here, these little beautiful round things called calcareous nanofossils, or coccolithophores. And you can see, the amazing detail, the amazing beauty, really, of some of these microscopic things, which they look to us like dust, more or less. But under a scanning electron microscope is just beautiful stuff, I think. Now, as it happens, all of these microfossils, these are some glassy ones here called radiolarians, and they're actually made out of opal, of all things, compared to the calcareous forms of the other types of fossils I just showed you. But in any case, they're all characteristic of particular times in Earth history because there's constantly been evolution going on in the deep sea. These things have evolved through time, and if we know the times at which various species have appeared through geologic history, we can then, of course, date those sediments in other places. So anyway, here we are. Here's Taniel back here in his microscope looking at radiolarians. And then we have regular visits from this fellow right here. This is Jochen Erbacher again. And he, as the co-chief scientist, was responsible for making sure the drilling operations went smoothly. And part of the information he needed was to know how old the rocks were that we were drilling so that he could make decisions about what to do next. And so with regularity, clockwise regularity actually, he would turn up and his smiling visage there would demand, okay, I want to know how old it is. And then when we'd start dithering a little bit, he would get very upset with us. All right. Now, after we got done with the core, it went up to the sedimentologists. And this is a sedimentology laboratory with a couple of interlopers here from the Paleolab. And the sedimentologists would look at the core, they'd describe it, and a number of other kinds of measurements would be made on it, and we'd all write reports on the various sites that we drilled, which end up being a volume about this thick. So we produce a huge amount of work, which then gets published, very shortly after the cruise returns to port. This is Radio Australia here, also known as Helen Bostock. We called her Radio Australia because she had the tendency of speaking very loudly and almost incessantly about whatever it was that sort of came into her mind. You get to know these little quirks of people, after a while. These sort of things kind of come out when you're at sea for 2 months. But in any case, she and Ken McLeod are looking at some of the cores that were the targets of our drilling operation. These are clay stones of Cretaceous age, about 90 million years old in this particular case, with these beautifully preserved fossils that we were out after to try to reconstruct ancient temperature records. And here's what some of those cores look like in detail. You'll notice that they're very finely laminated in some cases. This is characteristic of sediments that have been laid down in anoxic environments, places where there isn't very much oxygen in the bottom waters. And so all the usual sorts of benthic fauna down here, the worms and so forth that are stirring around through the sediment, aren't able to live in this kind of setting. And as a consequence, the little annual layers of stuff that's drifting down from the surface of the ocean and accumulating on the bottom is undisturbed, and you get this beautiful, very fine lamination. We also have other things like these are probably fish turds, coprolites we call them in science, that have been that also settled down through this quiet environment. Various kinds of fossils, including some beautiful examples of ammonites for those who are into fossils, relatives of the chambered nautilus, and so forth. And as it happens, these sediments look very similar to those that we find on land over in Morocco, a place called Tarfaya, Morocco. Here we have some more of these very finely laminated sediments exposed in this beach outcrop. You notice that they're dark colored because they have all this really organic, rich material that accumulated in this anoxic setting in the eastern tropical Atlantic. And this happens to also correspond to an important boundary in Earth history called the Cenomanian-Turonian boundary, which was a major extinction in the deep sea. It was also a time when, probably owing to the deposition of all this organic material that prevented it from being oxidized, led to a major increase in the amount of oxygen in the atmosphere, and probably also the incidence of wildfires and things like that as a consequence of an increase in oxygen. All right, so what we were trying to do fundamentally, this is my last scientific slide, okay, on this cruise, was to understand the temperature history of the past so that we could model the amount of greenhouse gases that were present during an earlier warm period of Earth history. This is a recent record of carbon dioxide for the last 400,000 years. We're sitting right over here, and this is what we've done to the atmosphere, okay? We've added almost 100 parts per million CO2, and we show no evidence of stopping that. I don't think that we're anywhere close to the 90 million year sort of scenario of several thousand parts per million, but we're definitely well on our way. And trying to understand the nature of the world by looking into the distant past to hopefully give us some idea of how the dynamics will work in the future is fundamentally what the ocean drilling program is all about. Okay, now there's a lot of stuff that you of course never hear about in the scientific discourse about ocean drilling or any other kinds of scientific endeavors. And so I'm going to give you a little bit of a flavor for the other aspect, okay, of being on a ship for 2 months. Here we have, of course, the stealth fighter. Okay. Very stealthy indeed. Okay. The other aspect, of course, is that, as I've mentioned before with Radio Australia, you get all sorts of insights, anyway, to the personalities of people on the ship. Here's my colleague, Hiroshi Nishi, who decided that the best thing to do was to create a bed for himself underneath his sample description table. And actually, many of us ended up trying this out. It was amazingly comfortable, even though you're lying on a steel deck here. We also had barbecues. This was a great sort of pleasure, actually, when you had the opportunity, was to get out in the nice sunny tropical climes, have a barbecue put on by the catering staff on the ship. And they did an absolutely fantastic job, amazing spread, as long as it wasn't too windy. We also had, at the very end of our drilling operations, a kite flying contest, competing the various labs and the drillers and the crew and so forth against each other. Here we have our co-chiefs emblazoned on this particular kite. And here's some of the audience. This was carried out on the helideck, the aft end of the ship, with all of us sort of standing around admiring each other's kites, trying to figure out which one would go highest and farthest and so forth. Some of the kites were amazingly complex little things with very fancy means of recovering them and so forth. This particular kite, however, did not fly. In fact, we put it over the ship and it went plonk into the ocean, just like that. Many of the other kites, for example, broke their strings and off they went. And as it turns out, it was the drillers who came up with the best kite that was able to get highest up into the sky, one that they had used before. This was my kite, okay. I built one. We were surrounded by mahi-mahi during this cruise. They used the ship as a sort of a congregation point. And so I've made up my mahi-mahi kite here, a big tube kite, with the tails that would flap nicely in the breeze. And I actually was able to recover it, which was unusual. And it was put to good work later on. Various people, unbeknownst to me at the time, had good fun with my kite. Here we have Hiroshi Nishi trying it out. The other thing that went on about the same time is that we were drilling just north of the equator, and we were due to sail south of the equator to Rio de Janeiro. And so there would be what is called the equator crossing ceremony on our particular cruise, which for those of you who have any familiarity with oceanography know can be, well, at least half the fun is the intimidation that goes on ahead of time. And so here we were all on the helideck, and here is various ladies' undergarments, okay, swiped from some of the female scientists and suspended from the mast pole. Things also began appearing as we got closer to the equator. We had the little equator crossing indication that, yes, it was coming up for those polywogs who had never crossed the equator, that they were going to get, you know, good treatment. And then this picture appeared too, which showed a French scientist of times past who had put up a particular struggle when he was forced to cross the equator. I was a polywog, I have to admit, okay? So I'd never crossed the equator before, at least on a oceanographic ship. And so I put up this little thing here. I'm just singing in the mud, because I wanted to indicate how non-intimidated I was, which of course wasn't really true. And other things began to happen too. This is Woody Wise emerging from his door, his stateroom that happened to be covered over with a big piece of butcher paper. And here he is coming all the way out. The butcher paper had also been stuffed full of these little cubes of styrofoam that we use to keep our cores damp. And so, in any case, it was Woody also, despite having sailed on something like maybe 10 legs or something like that, had never crossed the equator before. Hiroshi Nishi, my colleague in the Paleo Lab, was always a source of inspiration. And as it turns out that he had actually crossed the equator before, but he had never gone through the ceremony. And so nobody let him off the hook. He says here, "I am shellback, eat fly," he says. And I think the eat fly business is a reference to him no longer being a polywog, but being the next sort of stage of things. But as you see from his attire, we were asked to wear our underwear inside out and to sort of get appropriately dressed for the equator crossing ceremony. This consisted, you can see that this was a very involved sort of state of affairs, okay? This consisted of a visit from Davy Jones, reading his proclamation to all of us, and of course his mermaid or merman accompaniment, and of course the old sea dog here. And so here we are, all us polywogs gathered on the bow of the ship. And the shellbacks, okay, those people who had crossed the equator before, had in mind to wet us down with a fire hose. Now, they didn't realize, of course, that we were faced into the wind. And so you get the idea, okay? A gust happened to come up at a very felicitous moment, and it blew all the water that was supposed to be ladled on us back on top of the shellbacks, which, of course, we were very pleased about. Here we have Sheriff Bubba. There is supposed to be a sheriff, somebody who leads the polywogs around to the various events during the equator crossing. There he is, being properly sheriff-like. The first aspect of this was the breakfast, okay, in which we were doused with various table scraps. Here we are down here having stuff dumped upon us. And of course we managed to pick up that stuff and heave quite a lot of it back at them. And then, of course, a visit to His Royal Highness, the King Neptune, who is shown here. This is a very august fellow, actually. This is Phil Myers from the University of Michigan. He's an organic geochemist on our leg. And he happened to have the distinction of being a so-called golden shellback. Now, golden shellback, for those who don't know the terminology, is somebody who has crossed the equator at the meridian, of all things. So, in this case, in the eastern part of the Atlantic. We also have the baby here, and one of the things that you're supposed to do is kiss the belly of the baby. So they always try to find the sort of most overweight character that they can. He is also, of all things, a fairly august fellow in his normal times. This is Jürgen Thurau from the University College London. And then we have the barber over here and the mermaid accompaniment and so forth. Here is Jürgen, of course, preparing his belly to be kissed with liberal quantities of peanut butter and chocolate sauce. I had peanut butter up my nose for longer than I can imagine, actually, after this. And then here is the barber doing her thing on Radio Australia. Some of us were put in the stocks. That's me in the background right here, because we had put up somewhat of a fight along the way. And that's not considered to be, good thing, but they fortunately had this means of arresting our flight. And then, of course, there was also the final dunk to welcome us into shellbackdom in a bucket of very disgusting stuff. Okay. So in total then, this is what I got in the end. This is my little equator crossing card that indicates that I am now a shellback and able to inflict similar sorts of pain and suffering on polywogs of my own right. Now this particular cruise ended in Rio de Janeiro. And so here we are standing here looking at the city off in the distance. And I must say that on the whole it was a great fun. You know, it was nice to, it's a sort of one of these circumstances, you spend 2 months at sea with people, you get to know them obviously very well, and for me anyway, being with people from 9 different nations was an absolutely wonderful experience. You know, we think about international scientific cooperation in various, you know, big physics projects and so forth, but by God, you know, this is really the way to do it. You lock up people on a ship, you get to know their quirks, and you make friends for life. And I've now been involved in 4 of these different cruises, and I've enjoyed every one. I'll definitely do more of this kind of stuff in the future. And that's it. Thank you very much. Okay, how do I extract the fossils from the stone? Well, in some cases, it's just a matter of taking a lump of mud off the bottom of the ocean and washing it through a sieve. And that's very simple. We love that kind of thing.
Well, that's not
from way down there, yes. When it gets to be really hard stuff, then it gets to be challenging. And as you saw from my little beaker that was overflowing, we tried all sorts of different methods to try to break down some of these rocks to extract the microfossils. And we were only partially successful. It was only after the cruise we realized that just household bleach did the job beautifully. And so sometimes you just can't extract the fossils. That's just the way it is. The rock's too hard. And in that case, we sometimes cut thin sections where you take a little slab out of the rock and glue it onto a glass slide and then polish it down so you can actually see through that thin layer of rock. And then we can try to identify the fossils in cross-section. But most of the time, with the stuff that we were drilling, we were able to digest the rock in some way, either by boiling it on a hot plate sometimes, by using hydrogen peroxide or other kinds of nasty chemicals to cook the rock a little bit, which would cause it to fall apart. Paula over here, my technician in my lab, is undoubtedly quite familiar with the different techniques that one has to use for these things. But it's really a function of the nature of the rock and what kinds of processes you use. The sawtooth nature of that is from variations in global climate. As we've oscillated in the last, say, million years or so of Earth history between glacial and the current sort of interglacial type of climates. And as the ice sheets wax and wane on the poles of the planet, there are major changes, obviously, in the concentration of CO2 in the atmosphere. So there clearly is a natural rhythm, okay, and that what we're doing today is basically diverting away from that natural rhythm to some new state. Now, what consequence that has, this is still to be determined. Obviously, temperatures are rising above whatever the natural sort of rhythm would suggest. Who built the ship, who owns the ship, and what year was it built? Well, I don't know the answer to 2 of those questions. I think the ship was built in Halifax, but I'm not positive about that. And it is, it must be at least maybe 15 years old, maybe a little bit more than that. It used to be owned by Schlumberger, which is a big oil industry service firm, and they operate 3 or 4 of these vessels around the world. It is currently under lease. Actually, I guess it's still under lease. The program has actually ended as of now. But in any case, it was under lease by the National Science Foundation of the United States and has been funded through a consortium of science foundations around the world. So the owners, I think, is actually BP Petroleum still, maybe. I'm not quite sure about that. And they usually use these vessels for, of course, oil exploration. Now, the crew love to be part of the ODP because they have regular employment, whereas these other vessels that are used for the oil industries, they may have a job to do for a while, and then everybody gets thrown out of work for a bit, and then they go back and do it again, 6 months later or whatever. So it's been a wonderful vessel. It's been well decorated up by the various scientists. We all make our T-shirt logos that we plaster around on the vessel. And I believe it will be part of the next phase of this ocean drilling program, which is due to start this coming summer. Okay. The questions that arise from this particular vessel. Okay. So what questions light me up? Well, I mean, I'm interested fundamentally in the evolutionary process and also in the interaction between climate evolution and biological evolution on the planet. What really strikes me is that we were very successful in recovering a deep sea fossil record from this, what had really been kind of terra incognita, this interval between, say, around 100 million years ago up to about 48 million years ago, something like that. So a big, broad swath of time, we got a beautiful set of records from the tropical Atlantic to study evolutionary process and also the climate change that had taken place at the same time. So for me, I'm all hot to go, to see how these records evolve, because fundamentally, we have a sample currently every, say, 100 to 200 or 300,000 years, okay, currently from this time period. So we have a very kind of poor record of the sort of detailed variations in climate. And there's all sorts of stuff to discover, basic things. It wasn't very many years ago we discovered a major episode which people call the Paleocene-Eocene thermal maximum, a time when the world really got very warm over a very short period of time. It's thought that this particular event was caused by the massive release of greenhouse gases into the atmosphere and the ocean. And we didn't know anything about that just a little over 10 years ago. So by being able to produce these very detailed records of ancient climate, we're discovering very fundamental things about how the climate system and the biological systems of the world work. So this is a question of what caused the massive release of CO2 in this Paleocene-Eocene event, right? Well, we don't know the answer to that. In fact, I think that's probably number one question, is what caused that particular event. We think that the CO2 came from so-called methane hydrates, which some of you may be familiar with. These are it's actually ice that traps methane, which is a very potent greenhouse gas, in the crystal lattice. And these hydrates are found abundantly in permafrost and also in parts of the deep sea. And it's hypothesized anyway that that was the source of the methane and the CO2 that caused the global warming. But the problem is, we don't know how it gets out. What is the trigger for releasing this stuff from the deep sea? That's still fundamentally a mystery. Right. I mean, what some people have proposed that there was a meteorite impact that caused that basically disrupted a lot of these reservoirs, allowing gas to escape. Others, including myself, have proposed in the past that something triggered the major failure of one or more of these big reservoirs, and that got the whole cycle of warming, more failures, more warming, going. But I actually am not sure that I believe that anymore. So, that's what you don't understand is how something basic like that gets going. Here we're thinking about tapping methane hydrate as a potential source of energy. There's massive amounts of energy preserved and contained within some of those hydrate reservoirs, and yet we don't know the first thing about what their geologic record of effects on climate change really are. So I would suggest that we really ought to have a better idea, what the dynamics are before we go monkeying around with them. So the question is this totally unrelated to the time when the Atlantic was much narrower and there was, the beginning of rifting of the Atlantic? The answer is no, that it's not unrelated, in the sense that, that the time period when the deep Atlantic became an anoxic basin, okay, very much like the modern Black Sea, was a time when the Atlantic was a much narrower basin than it is today, say 90 million years ago. And this was also a time when, because of the lack of oxygen in the deep North Atlantic, we were able to preserve all this organic gunk that fundamentally changed the climate system of our world by locking up a lot of this carbon in the form of organic material that would otherwise be oxidized and just participate in the normal climate carbon cycle. So the things probably are related, would be my guess. And it's interesting that, at that time in Earth history, when the Atlantic was a fairly enclosed basin, that you're able to drive it completely anoxic for a long period of time. Basically, the bottom of the Atlantic was a dead sea. And that's also kind of a striking thing, too, to think about how much the world has changed over time as a function of tectonics and also climate. Okay, what is the diameter of the drill hole? The drill pipe itself is about yay big around, okay, and it's a hollow pipe. The core that it cuts, of course, the drill pipe wiggles around in there a little bit. Those bits are about yay big around as well. They cost about, say, $7,000 to $11,000. Okay, they're sort of like an old Volkswagen Beetle used to, be about that same price. And they drill a hole that is ideally sort of around that same diameter, but typically may be a bit bigger. And so the core itself that we drill, it's about this big around. And for those who want to look at them, we have them down in the SIO core repository, or you could also visit the Ocean Drilling Program repository right next door. Okay, what holds the vessel on site? This is one of the most amazing things to me about the whole business. We can drill in high winds, high sea state, and so forth, because the ship is held in place by a series of thrusters that are controlled by a computer system that in turn has a GPS navigation system. And the thrusters consist of big propellers that are lowered down in shafts. I don't remember exactly how many there are, maybe 6 or 8 of them around the ship, up in the bow, the stern, and on the sides. And these things are computer controlled, so they can keep the ship located over the drill hole within, say, 5 to 10 meter spacing. So, if the drill hole was in the middle of the room here, the ship 3 or 4 kilometers up there would be located, within the space of this room.
That's
yeah, the pipe, it's flexible. It's like a big piece of metal spaghetti, more or less, when you get such a lot of it. There was an accident many years ago during the very beginning of the so-called deep sea drilling program, and they had the pipe break off at the ship. And I think they were drilling in around 5-6 kilometers of water, so they lost that much pipe, and it sank to the bottom of the ocean. And when they went back to look at it later on, they could see it was coiled up like a big piece of spaghetti. Pipe that big around. That's amazing. But that's what happens when you have however many thousands of tons of pipe that you're dealing with. Okay, so the question is whether there have been cycles of evolutionary development like the temperature cycles that we observe. That's actually what got me into this whole field, was recognizing that over the past, say, 100 million years of Earth history, the little microfossils that I work with, they do show this beautiful cycle in terms of the diversification of different sorts of body styles and probably ways of life. They don't seem to follow climate systems very much, okay? So there seems to be a lot of independent evolution from climatic evolution to some extent. And it's true also that when you look at those, like the 400,000 year record I showed, that they're really, species don't track that particularly well because evolution works on a longer time scale still. But it is fascinating to think about what have been the controls on evolution. And certainly one of them have been the periodic mass extinctions that have happened over the past 100 million years. For example, the Cretaceous Tertiary boundary 65 million years ago was this meteorite impact event that is thought to have killed off the dinosaurs. That basically reset the evolutionary process. It got rid of a whole lot of incumbents, more or less, species that had already figured out ways of doing things. They all got bumped off, and then you had to recreate that all over again. And amazingly, life did recreate a lot of that same diversity, that same basic way of life. I mean, isn't that amazing somehow to think that it's kind of, we talk about extinction is forever, and that's certainly true on a human time scale. The loss of biodiversity we face today is going to be with us for all of the foreseeable future of humankind. But on geologic time scales, on millions of years, it's very likely that many of these sorts of ways of life will re-evolve that are being lost now. And they may be a little bit different than what we have now, but I have every belief anyway that there will be the expansion of life's diversity once again after this most recent mass extinction. Okay, so the question is about the evolutionary history of the siliceous versus the calcareous microfossils that we work on. Those siliceous organisms, the radiolarians, are another group of animal protists. Okay, they eat other things for the most part. Many of them are also little farmers of the ocean in that they have symbiotic relationships with algae and they farm these algae as part of their life cycle, which also happens to be true for many of the planktonic foraminifera that I work on. The siliceous fossils go way back in evolutionary time, back into the early part, say 400 or 500 million years ago, is when we first find these siliceous organisms. The calcareous planktonic foraminifera that I work on also have an equally ancient record. And they're probably both participants in the original diversification of large-bodied life on the Earth in the early part of the Cambrian, although our record is somewhat spotty about that. So they've been around on the planet for a long, long time and have been participants in creation of things like the chert nodule, which is sitting over here, which has affected basically the storage of silica in the oceans, which is an important nutrient. So yeah, they have a very ancient record. Okay, so would I expect to get the same sort of temperature record from the Pacific as we are developing anyway from the tropical Atlantic? The answer to that is yes and no. I mean, clearly there are variations in climate today from place to place. The tropical Western Pacific, for example, is a much warmer place today than the Eastern tropical Pacific. And so there's going to be some variation, and therefore we can't expect our records to be emblematic, essentially, of the whole tropical ocean everywhere. But nonetheless, we do expect that the variations that we observe, the major cycles and changes in tropical climate that we observe in our Atlantic cores, hopefully will give us some indication of what's going on elsewhere in the tropics. And the tropical Atlantic area where we were drilling is probably also one of the warmest parts of the tropical Atlantic. And so it's a good place to measure what's going on in terms of tropical climate. But it is not emblematic of every place.
I think we're going to have to stop there. I'm sure if you have any more questions.